Now I will start discussing chapter 3 and chapter 3 about pressure and fluid statics. So now I'm going to start discussing what do we mean by pressure in this lecture, and later on I will start to talk about pressure measurement devices. So the main objective of this topic of this lecture is to talk about pressure. So let me start with basic questions. What is pressure? What do we call pressure when speaking about solids? And what is the unit of pressure? These are simple questions just to remind you about this subject matter. Now you know that pressure is defined as the normal force exerted by a fluid per unit area. So P is equal to F over A. You know this. We speak of a pressure only when we deal with a gas or a liquid. So pressure is caused by gases and liquids. However, the counterpart of a pressure in solids is the normal stress. So if we have solids, we don't talk about pressure, we talked about normal stress, which is equivalent to pressure when we talk about solids. Now we know this since pressure is defined as force per unit area, so it has the unit of newtons per square meter, Newton per meter square, which is called Pascal. So Newton per meter squared is called Pascal, and this is the unit of a pressure in the SI system of units. Now, when we are talking about pressure, usually we talk about two types: absolute pressure and gauge pressure. So what's the difference between them? Now let me go through these slides with you. So the actual pressure at a given position is called the absolute pressure. And this absolute pressure is measured relative to what is called absolute vacuum. Okay? Actually, most pressure measurement devices, they are calibrated to read zero in the atmosphere. So if you look at, for example, any of those pressure measurement devices, you can see that they are reading zero because they are calibrated to read zero in the atmosphere. And so they indicate the difference between the absolute pressure and the local atmospheric pressure. So they will give the difference between the absolute pressure and the local atmospheric pressure. Usually this difference is called the gauge pressure, okay, the gauge pressure. Now, a question to be asked here is, can the gauge pressure be negative? If it can be, if it can be negative, what do we call it? So can gauge pressure be negative? If it can be negative, then what do we call it? What is the special name of it? So pressure, P gauge can be positive or it can be negative. Okay, so P gauge, it can be positive or it can be negative. But pressures below atmospheric pressure are sometimes called vacuum pressures. So if we have pressure that is lower than atmospheric pressure, the gauge pressure is called vacuum pressure, and they are measured by vacuum gauges. And again, that indicates the difference between the atmospheric pressure and the absolute pressure. Let us look at this figure here. So suppose I have, let me start with this. Suppose I have this one, P absolute is equal to 0, which is this, which corresponds to absolute vacuum. So the absolute pressure, you know, it will be equal to the P atmospheric, which is from here to there, plus P gauge, which is from here to here. So P absolute is the total of them. You look at this equation, B absolute is equal to B gauge. You take this the other side, plus P atmospheric. However, if the gauge pressure is less than the atmospheric pressure, then you have something like that. So B absolute in this case, as you can see, is equal to P atmospheric minus B gauge, okay, or B vacuum here it is called. So B absolute, you can take it here, you take this the other side. So B absolute is equal P atmospheric, as I have just told you, minus B vacuum or B gauge. You have studied this before, I'm just reminding you about it. Now, throughout your textbook, which is Chingle and Kimbala, the P will be denoted, or it will denote the absolute pressure. So whenever P is mentioned, it is meant to be absolute pressure, not gauge pressure, unless specified otherwise. And sometimes also, often the letters A, okay, is indicative of absolute pressure, and the letter G is an indicative of the gauge pressure. So in the English system of units, when we write PSIA, then we mean pound force per square inch absolute. PSIA is pound force per inches square absolute, okay? And when we write PSIG, then it is pound force per inches square, but here we are talking about gauge. So A stands for absolute, G stands for gauge, and PSI stands for pound force per square inches, which is the unit of a pressure in the English system of units. And I want you to practice by solving example 3-1, which is about absolute pressure of a vacuum chamber. Now, a simple question to be asked: does pressure increase or decrease with the depth of the fluid? So as you go down, for example, suppose this is a fluid here, all of this is a fluid, as you can see, and if I go from this point to that point, from point 1 to point 2, from P1 to P2, does the pressure increase or decrease with depth? Another question is, now, the variation of pressure with depth, is it linear or exponential or what? So suppose you told me that the pressure as I go down, it increases. So does it increase linearly like this, for example? Or does it increase in, for example, an exponential way like that? Or how? So how does it, I mean, is it increase or decrease? And how does it increase, linearly or not linearly? So again, I want you to consider this. So we know that, actually we studied that as you go down, the pressure increases, and it increases linearly according to this equation, okay? According to this equation, you know that P is equal to rho GH. So as we increase H, as you increase the head of the fluid, the pressure increases. And this equation is an equation of a straight line, okay? So you can say that the pressure increases, so in other words, pressure in a static fluid increases linearly with depth. And you remember this equation that delta P is equal P2 minus P1, which is equal to rho G delta Z, or delta H in this case. And I can replace rho G with gamma. Remember this? Remember it, specific volume from chapter 1 and chapter 2. So I can write delta P is equal to gamma delta Z. And delta Z is the difference in height of the fluid, which is the same as delta H, or whatever you want to call it. So let me read this with you. The pressure difference between 2 points in a constant density fluid is proportional to the vertical distance Z between the points and the density rho of the fluid, okay? And the density rho of the fluid. Also, remember this from previous courses. So now, pressure in a fluid increases with depth because more fluid rests on deeper layers, and the effect of this extra weight on a deeper layer is balanced by increase in the pressure. So as I go down like this, the pressure increases. Okay, the pressure increases, and this pressure increases linearly with depth. So this is the pressure caused by the fluid, as we said, as the gauge pressure. Okay, is the gauge pressure. This is the pressure caused by the fluid. Now consider I want to think about the if I have variation of pressure with depth in a room full of air, how to handle it. Suppose I want to consider the difference in the pressure in your room at the ceiling and at the floor. Okay, does it make a difference? Is the difference in the pressure very large or is it small? Can I neglect it? Let us ask this question. So to answer it, actually, suppose this is your room. Okay, this is your room where the pressure at the top is 1 atmosphere, the height of the room is 5 meters, and the pressure at the bottom of the room is 1.006 atmosphere. So as you can see, the difference in the pressure is very small between the top and the bottom of the room. So we can say then the difference in the pressure through, let us say, a gas like air in this room is negligible. So you can consider the pressure to be constant everywhere in the room because the density of air is very small. The density of air is very small. Let me read the slide with you. The pressure in a tank containing a gas, for example, can be considered to be uniform since the weight of the gas is too small to make a significant difference. Because the density is small, the weight of the gas is not that much to be considered. It's not going to affect, let us say, the pressure that much. So also the pressure in a room filled with air can be assumed to be constant. So in a room that is filled with air, I can say that the pressure everywhere is the same because the density of the air is small, so it will not have a great effect on pressure. Um, Now this is also a nice slide, an important slide. Let us look at what we have here. So suppose I have this container that contains, for example, a liquid. The pressure at the top P1 is equal to P atmosphere. This is the pressure at point 1, which is the atmospheric pressure. Suppose I ask you what's the pressure at point 2, P2. And suppose I ask what is the absolute pressure at P2, not the gauge pressure, the absolute pressure. Okay, so if we take the point 1 to be at the free surface of the liquid open to the atmosphere, where the pressure is the atmospheric pressure P atmosphere, then the pressure at the depth h from the free surface becomes what? So P2 is equal to what? P2 here is equal to P1, which is P atmosphere, plus rho GH, okay? Rho GH. So this is P2 now, P absolute. If I ask you, what is, for example, P2 gauge? If I ask what's P2 gauge, then this one will be equal to 0. So it will tell me P2 gauge is equal to rho GH. Okay, without considering the atmospheric pressure. Okay, so this is the answer. This is what I have just talked about. So P is equal P atmospheric plus rho GH. And here P gauge is equal to just rho GH. Okay, just rho GH. Now suppose I have this funny shape. I have this container with a funny shape. And as you can see, I have P atmospheric at the top. It is full of water. But here I have little bit of mercury. And you know that the pressure is changing linearly with depth. Okay, so now suppose I ask you what is the difference in the pressure between points A, B, C, D, E, F, and G. What will you tell me? You might tell me that the pressure at these points are the same. All the pressures are the same. But now suppose I ask you Which one got a higher pressure, point H or point I? Which one has more pressure? Okay, you will tell me point H got more pressure because there is some mercury here which is resting on point H, but the point I is just resting underwater. Okay, it's resting underwater. So H got the most, let us say, pressure, then I, and then all of those points here from A to G, they have the same pressure. Now let us just give you the conclusion of the previous slide. So pressure in a fluid at rest is independent of the shape or the cross section of the container. So as you have just seen that all, let us say, the points on the same elevation, you got the same pressure. It changes with vertical distance, but remains constant in other direction. So if I go down, the pressure increases. If I go up, the pressure decreases. But if I just go horizontally, then the pressure remains constant. Therefore, the pressure is the same at all points on a horizontal plane in a given fluid. Okay, in a given fluid. So again, this is what I have just said in the previous slide. So note that the pressure at points A, B, C, D, F, and G are the same since they are at the same depth and they are interconnected by the same static fluid. So I want you to write this note. I mean, every time that you are going to solve a problem and you are using, let us say, the fluid statics, and you want to use, I mean, the concept that 2 points have the same pressure, you have to tell me this. In a static fluid, this is a static fluid. All of this is a static fluid. Okay, I want to change the color. So all of this is a static fluid. So whenever you want to use this concept, you will tell me in a static fluid, 2 points at the same fluid, okay, and they are at the same elevation, connected by the same fluid, they have the same pressure. Again, for example, D and E will tell me that the pressure PD is equal to PE. You have to tell me why. And this is because in a static fluid, 2 points at the same elevation, connected by the same fluid, they have the same pressure. Okay, they have the same pressure. On the other hand, however, the pressures at point H and I, as I said, H and I, those 2 points, not the same, since these 2 points cannot be interconnected by the same fluid. So I cannot say pH is equal to PI. This is wrong. Why? Because they are, even though they are at the same elevation, but they are not connected by the same fluid. So the fluid is static, they are at the same elevation, but because they are not connected by the same fluid, they cannot have the same pressure. Okay, they cannot have the same pressure. So the important concept, again and again, whenever you have a problem where you have to solve it, I mean fluid statics, where you have to equate the pressure between the 2 points, you have to tell me this concept. They are equal because it's a static fluid. These 2 points are at the same elevation and they are connected by the same fluid.